Hey guys, hoping all is well with everyone. So in this video we're going to be continuing on with the 8th grade Common Core Curriculum Guided Practice. And again, I wanted to kind of put this together just to, as a response to COVID and just being able to give students a supplemental that will help them and give a step-by-step approach to a lot of these Common Core concepts. So this is going to be a continuation with Module 1. This one's going to be Module 1.2, Sets of Real Numbers. So what this section talks about is being able to categorize numbers by their attributes and properties to be able to put them in a certain categories, so to speak. So what we're going to be doing is looking at these different values and putting them into their respective categories based on their properties and attributes that they uphold. With this one, we're going to be taking verbal sentences and scenarios and deciding if they're true or false statements based on the relationships that these categories and sets of numbers have. The third one is going to be using real life situations and categorizing those values based on the situation that is described. Okay? So what they want us to do for 1 through 8 is look at the value and determine what category or what set of numbers they belong in. So just as a quick recap, the possible choices that we have, if we were to make a Venn diagram of this, all whole numbers are going to be at the very core of the circle here. So all whole numbers are rational numbers, all integers are rational numbers, and then irrational numbers are their own kind of category. Remember, irrational numbers are numbers that cannot be expressed as a ratio or fraction of two integers. They do not terminate, or they don't show a repeating decimal pattern. Okay, big examples of irrational numbers are pi, your mathematical constant 3.14159, on and on and on. And exponential e as another example. So let's go ahead and start with number 1 here. So 7/8. So 7/8 is a ratio of two integers. So that's going to make this a rational number. Okay. Now it's not an integer because it's not a whole number, or it's not an integer. So we're going to call this a rational number. Okay. The square root of 36. Now this one's a little tricky because it can be plus or minus 6. Remember, when we take the square root of a value, we're going to end up with the positive and negative of that, because we're going to end up with, if you square a negative, you end up with a positive. So this is going to be integers and whole numbers. Okay, so remember, because 36 is a perfect square, that means that its square root, it will be an integer or a whole number. The square root of 24, so this one is a little interesting because it's a square root. 24 is not a perfect square, so the square root of 24 is approximately 4.89897948, but as you can see, based on that, I'll actually type it out here, 89897948. So as you can see, there's no pattern to this that repeats. It doesn't show that it will terminate at any time. So this is going to be an irrational number. So remember, irrational numbers are going to be numbers that cannot be expressed as a ratio of two integers or whole numbers. Okay? If you wanted to break this up, the square root of 24 is going to be, so if you do the prime factorization, just to kind of go in depth here, the square root of 24, if you do its prime factorization, it's going to be equal to the square root of 2 times 2 times 2 times 2 times 2 times 3. So that's going to be equal to, if we take out a 2 squared, it's going to be equal to 2 root 6. And the square root of 6 is going to be 2.44948,974. So we'll see that this is an irrational number because it can't be expressed as a ratio of two integers. Okay. For number 4, 0.75. So 0.75 is going to be a rational number. It can be expressed as two integers. What we would do there is we would multiply the top and bottom. So keep in mind that any number is itself over 1 at any time. If we multiply top and bottom by 100, this will give us, again, that multiplicative identity of 1, where I'm not changing the value of 0.75, I'm just changing the way it's expressed. So this will give us 75 over 100, which is indeed a ratio of two integers, making that a rational number. Okay. Let's look at 0. 0 is interesting. 0 is a whole number. It is not an integer because 0 doesn't take sides of a negative or positive characteristic. It's just the base of the number line. So again, it doesn't take a positive or negative attribute or characteristic at any one point. Okay. Negative, the square root of 100, that's going to be an integer. And the reason for that is the negative, so the square root of 100 is going to be 10, but since we're going to be applying the negative to it, that's going to be negative 10. So it's still going to be an integer. It's a whole number as well. Okay. Keep in mind that the biggest difference between integer and whole numbers, integers are whole numbers that just carry a positive or negative attribute to them. And that's all that integers are. So don't overthink it too much when you're trying to differentiate them, because if you have an integer, it's automatically a whole number. So like I said, if you were to look at a Venn diagram, you have the whole numbers in the very middle, and then you have the integers on the outside of that. So all whole numbers are integers because they're encased in that integer category. Okay. 5.45 repeating. This is going to be a rational number. Remember, one of the key characteristics of a rational number is it can if it can have a repeating decimal. So this would be 545, or I'm sorry, if we were to write this as a ratio of two integers, what we would do is do 5, and then what we'd do is a way to represent 45 as a repeating decimal. So this would be 4.45 is equal to 100, or 100x. We would subtract x from both sides, as we did in the last section, which would give us that 99x is equal to 45. So it would be 5 and 45 99ths. So this would be a rational number. And then negative 18 over 6 is going to be a whole, it's going to be an integer and a whole number. Reason being is, even though this is expressed as a fraction, negative 18 over 6 results in a whole number or integer product being negative 3. So that's going to be both an integer and a whole number. Okay? So just as a quick recap, rational numbers are fractions. They can be addressed as a ratio of two integers. Integers are just whole numbers that now carry the characteristic of a positive or negative value. Whole numbers are just numbers that do not have a decimal point addition to them. They are just whole numbers. And then irrational, and that sounds kind of redundant, but whole numbers are just numbers that don't have any decimal characteristic added on to them. Irrational numbers, again, are just numbers that cannot be expressed as a ratio of two integers, and these are numbers that do not terminate, or they show no repeating decimal pattern. Okay? Alright, now let's look at these two statements and decide if they are true or false, and explain your choice. All whole numbers are irrational numbers. That is very true. So if you think of a Venn diagram, if you think of irrational numbers as like the very outer edge of, like, if you think of like the earth, so to speak, you have the crust on the very outer edge, and then you have the core and the mantle in the middle. So think of like the mantle as whole numbers and the crust as rational numbers. So all numbers, all integers and whole numbers are rational numbers. Okay, because we think of whole numbers and integers as we can always just express them as themselves over 1. So this is true. All whole numbers are rational as they can be expressed as their value over 1. So remember, any number is just itself over 1. No irrational numbers are whole numbers. So what's this asking you is that no possible irrational number is a whole number, and that is very true. So no irrational numbers are whole numbers. It's almost like worded kind of weird or strange. So you want to be careful with these verbal ones too, because just the way it's worded. So, because if it said irrational numbers are whole numbers, that would be false. But since it says no irrational numbers are whole numbers, this is true. Irrational numbers are numbers that cannot be expressed as any possible ratio of two integers. Okay? Alright, let's look at the next section here. Identify the set of numbers that best describes each situation. Explain your choice. So the number 11 says the change in the value of an account when given to the nearest dollar. So what this means is, think of kind of like at the bank, where you either make a deposit or a withdrawal, and it's going to be to the nearest dollar, so they're going to be whole dollars. What that means is there's going to be no cents involved, so these are going to be whole numbers. But since this is possible changes in the value of an account, accounts can be deposited or withdrawn, which means that they have both positive and negative aspects to them. So because of that, we're going to say that these are integers and whole numbers. Make this explanation. Sorry, I might have spelled explanation wrong there. But the explanation is that with accounts, both deposits positive and withdrawals that would be negative can occur, and since it is to the nearest dollar, no cents or change will result, avoiding decimals. Okay, the markings on a standard ruler, so that is going to be representing a fraction of an inch or a centimeter or whatever metric unit that we are in question. So because of that fraction, it's going to be a rational number, being that the fraction on any point or marking on any marking will represent a ratio of two integers in respect to the next unit. So what I mean by that is, if we had 1/16 of an inch, that's going to be 15/16 units away from the next nearest whole unit. So because of that, we can represent these as a rational number being a ratio of two integers. Okay. Alright, so our last question here is, what are some ways to describe the relationships between sets of numbers? So, if we think of the Venn diagram here. So again, let me go ahead and actually draw you what the Venn diagram would look like. This won't be the best, but I'm going to do my best here. Okay, so at the very edge here, you're going to have your rational numbers. Here you're going to have your integers, and here you're going to have your whole numbers. Okay, and then over here, in its own kind of category, are going to be your irrational numbers. So this is kind of what I was mentioning by, if you think of it like the Earth here, we see that all whole numbers are both integers and rational numbers. So we'll go ahead and put that. All whole numbers are integers and rational numbers. We can also say that all integers are whole numbers. No irrational numbers can be integers or whole numbers. And the reason for that is because they can't be rational either, so that automatically knocks them out of being possibly integers or whole numbers. Okay, so those are a couple of the relationships that we can look at here. But that is the last question for section 1.2. I hope this helps you guys out. If you have any questions regarding this section, please don't hesitate to let me know, or if you have any requests for any sections in particular, please don't hesitate to request. But I hope this helps you guys out. Please take good care and be safe during this time. But I hope to see you guys soon, and thank you so much for watching. Take good care. Bye.